So this is lecture 1. It's the first of 11 lectures for ELEC270, signal classification. So just to give you an idea of where we are in the module, we have 11 lectures in total. There are going to be 12 teaching sessions, but 11 lectures. So this is our first lecture, signal classification. Next week, we'll look at signal operations, then Fourier series, Fourier transform, properties of the Fourier transform, and then our final lecture about signals, we're talking about sampling and discrete time signals. Now, the latter half of the module will be looking at systems. We'll start again with classification of systems, and then we'll look at Laplace transform and impulse response. Then we'll look at discrete time signal processing, and then further Z transforms. Okay, so discrete time signal processing will introduce the Z transform, and then we'll look at inverse Z transforms in our final week. And then in week 12, we'll have a revision session where we will prepare for the exam. So we'll look at some exam style questions. So that's the plan for the module. And every lecture, I'll present this again just to show you our journey through the module. Now, as I said in the module overview, it's an intense module with a packed schedule. So every week we have something happening. So every week there's going to be a lecture like this, pre-recorded and made available to you on Monday or Tuesday. So this is lecture 1, L1, made available on the 12th of October. So this is your introduction module, signal classification. Now, next week, we're going to talk about signal operations, Fourier series, etc. So this column is the column we just spoke about. These are the actual lectures. Now, what happens at our live sessions at 11 o'clock on Monday is different. So this morning, on Monday, the 12th of October, we had our introductory session. Well, we just had a little overview of the module. But next Monday, on the 19th of October, you have your first class test. So it's an online open book home test. I'll give you more information about that later, but that'll be your first test. That'll be next week. And that happens every other week. So on even weeks, you'll have a home test. So there are 6 in total, 6 open book online home tests. And each test will test the learning in the previous week's lecture. So in week 2, we're going to have lecture 2, but the test will only test you on the material from lecture 1. In week 4, you're going to have lecture 4, but the test will be about lectures 2 and 3. Same in week 6, you're going to have lecture 6, but the test will be about lectures 4 and 5. So you always have a week to prepare for the class test. Okay, so this is the schedule for the module. The same slide is up on Canvas. So I suggest you make a note of this. Okay, this is really important because if you miss a class test, there's no repeating it. So, a summary of the schedule. On odd weeks, we're going to have a problem class at 11 o'clock. We'll have a pre-recorded lecture, and we'll have problem sheets, solved problem sheets for you to go through. On even weeks, you're going to start the week at 11 o'clock on Monday with a home test. Then you'll have a pre-recorded lecture with the following week's material. Okay, so this is the schedule. All odd weeks, we're going to do problem classes. All even weeks, we're going to have class tests. So this week, we've already done the module overview. I've given you an idea of what the module is about. I'm going to start by talking about signal classification and elementary functions. We'll go over elementary functions again next week, but we're going to focus on signal classification. Problem class 1, problem sheet 1. Problem sheet 1 you'll find available online. problem class 1, that won't happen until the week after next. So what do we mean by a signal? So in engineering, a signal is any measurable variation of some quantity that's meaningful to us. So a variation of a measurable quantity that conveys information about the behavior of a system. It could be the temperature in the room. It could be the height of liquid in a tank. It could be the pressure. It could be the conversion rate of a currency against another. It could be the Dow Jones index. Any variation in a measurable quantity that conveys information we refer to as a signal. Now, a signal can be a function of time, or it can be a function of spatial dimensions, or it can be a function of something else. In this module, we will focus on signals as a function of time. That's simply because it's the most common type of signal, and it makes all our processing and all our course content coherent and meaningful. But a signal can be anything else. So an image is a two-dimensional signal, and the two dimensions, X and Y, are spatial dimensions. They're not time. But a signal can be a variation in time. So an audio signal, my speech right now, is a variation in time. So the horizontal axis is time. But it doesn't have to be. So a ripple in a ripple tank, or a ripple or a wave on water surface, can be a function of time and space. So it can be 2, 3, 4, 5 dimensional. But we're going to look at one-dimensional signals, where they are functions of time. Okay, so that's the first part of the module, signals. The second part is systems. What do we mean by a system? So in engineering, we refer to systems as entities that manipulate one or more signals, usually to accomplish some kind of function, and usually producing further signals. So it could be something like a communication system. It could be a hydraulic system. It could be the braking system in your car. It could be the navigation system in your car. It could be a GPS system. It could be a biomedical system. Here we have a little pacemaker. It could be a biological system. It could be a combination of all of these, right? So you will come across all the time. So you're probably studying another module, ELEC270, instrumentation and control. And that's just a short form of instrumentation and control systems. So it's an instrumentation system and a control system. So in engineering, almost everything you deal with is going to be either a signal or a system. So why is that important? Why are we interested in signals? Because everything can be represented as a signal. And these signals we use to make decisions. Because the signals themselves, remember we said they're measurable quantities that represent variations, that convey information. So it's the information that we're interested in. So now I'm speaking and you're listening. You're interested, I hope, in the information that I'm trying to convey. So the signal conveys information. That's why it's important. And by understanding the signal, by analyzing these signals, we can understand certain aspects of the signal that may not be apparent just by looking at it. Okay, so we will be looking at certain properties of signals in this module that will allow us to automate certain tasks. It will allow us to do things that we wouldn't have been able to do without these tools. So every time you speak to your smart speaker and you ask it to turn the lights on or to play some music, every time you have some automated voice recognition or automated character recognition or image analysis or video processing, remember what's happening is some kind of analysis of a signal. So you have a system that's making a decision based on some aspect of a signal. And to do that, we need to understand how to represent signals. And in today's lecture, we'll talk about how to classify these signals. So, signals are inputs to systems, and systems make decisions. So look at this video. This is a few years old. This is a video from the inside of a Tesla Model S, or is it a Model X? I can't tell. But what's happening here? So what we have, as far as the driver is concerned, is autonomous driving. Okay, so that driver isn't touching the steering wheel, but the car is navigating itself. You can see the brake pedal being pressed without the person's foot on it, and it's making decisions. But how are these decisions being made? What you have is a large number of sensors. So you've got cameras, you've got radar, LiDAR, you've got lots of sensors trying to make sense of the environment, trying to determine range and distance, using the velocity, using the navigational mapping information, trying to make decisions to best navigate the vehicle. Okay, so signals and systems have some very real and exciting applications. So today we're going to look at different classifications of signals. We're going to look at analog versus digital signals. We'll look at deterministic versus random signals, periodic versus non-periodic signals, discrete versus continuous signals, and power versus energy signals. Each of these has a specific definition, and we'll try to explain these by looking at a series of examples. So analog and digital. These words aren't new to you. You're familiar with the terms, and you're probably familiar with applications, and you probably know what it means. But specifically, when we talk about signals, we are interested in the number or the vertical axis. We're interested in how many values that signal can take. So if we consider this signal to be a voltage signal, potential difference, then this potential difference, this voltage, in an analog signal can take an infinite number of values. So it's totally infinite. That doesn't mean the range is infinite. It doesn't mean it can vary from minus infinity to infinity. It might be limited from minus 2 volts to 2 volts, but there's still an infinite number of possibilities between minus 2 and 2. So because there's an infinite number of possible values, we consider that an analog signal, as opposed to a digital signal where you have a finite number of values. In this case, it's simply either a high or a low. That could be 0 or 1, or it could be 0 and 50 volts. But the point is, it's a finite number. That could mean 2 levels, or it could mean 4 levels, or it could mean a million levels. But as long as it's less than infinity, as long as it's a finite number of levels, as long as the number of levels is finite, it's limited, then that represents a digital signal. Okay? So these are examples of analog signals and digital signals. There's another kind of signal, or another variation, another classification. What's a distinction between continuous time signals and discrete time signals? Continuous time signals, these are defined for all values of time, at every instant of time. So time is a continuous variable. In a discrete time signal, the signal is only non-zero, it's only defined at specific instances in time. So time is not continuous, it's discrete. It's like the New York Stock Exchange. It closes every day. So every day it closes at 5 p.m. A particular time. That value is discrete. It's not continuous, it's discrete. So here we have examples. So this is data that I collected using a ground penetrating radar. So this is part of research I carried out a few years ago. So that orange box there contains a radar. And that radar, instead of pointing to the sky to look at aircraft, it's pointing into the ground, looking at buried pipes, buried utilities. So that reflection there, that is a continuous time signal representing a radar return. What you see down here is a discrete time version of a similar kind of signal. It's discrete in time. Notice that it's only defined, it's only non-zero at specific moments in time. So this is called a discrete time signal. So discrete time signals, that's a different class of signal. And in this module, we'll be looking at both. So the first 4 weeks, we'll be looking at continuous time signals, then we'll look at discrete time signals. So a continuous time signal is defined for all values of time. Discrete time signal, it's the result of something called sampling. And we won't look at sampling until week 6 or 7. But this is what sampling does. It takes a continuous time signal and gives you a discrete time signal. Which of these two is digital? Now you might think, oh, the discrete time signal, that's clearly digital, and the continuous time is analog. But actually you'd be wrong. They're both analog. These are both analog signals. Unless they've been digitized and quantized, we consider both of these analog, because each of these samples could have any value or an infinite number of possible values within the permitted range. So that could be 6 volts, it could be 6.6, it could be 6.62. There's an infinite number of values that each of these samples could have. So they're both analog. So a discrete signal can be analog and a digital signal can be continuous. The opposite is also true. You can have a digital signal which is discrete, and you can have a continuous time signal which is digital. So this is how we represent a discrete time signal. So generally, in this module, at least, we will use square brackets to represent a discrete time signal. So normal brackets is just for t, so x of t. X of square brackets, that's where we use discrete integers. So x of 0, x of 1, x of 3. We don't use anything other than an integer there. So here t would be an integer, 0, 1, 2, 3, 4, 5. So that's just a little bit about notation. The next distinction we make is between periodic signals versus non-periodic signals. A periodic signal is a signal that repeats itself. So it has a period. So x at any point in time is repeated. It's the same after a fixed period t, uppercase T. We call that the period of the signal. So the period is t. So for example, x of 5 would be x of 5 plus t. If that applies for all values of t, lowercase t, we call that a periodic signal. So the fundamental period, or the period of the signal, is the smallest value of t. Smallest value of uppercase T for which that holds. And if you take the reciprocal of uppercase T, that means 1 over uppercase T, that is something called the fundamental frequency. So the fundamental frequency, F or F naught, is 1 over T. It's the reciprocal of T. That only applies if it's a periodic signal. If the signal isn't periodic, obviously it wouldn't have a fundamental frequency. So for example, which of these signals is periodic? So if this was a live session, if I was in a lecture theatre, we would probably have an interactive application where you could actually answer these questions and we can go through it. But in this pre-recorded session, all I can do is just talk through it. So which of these is periodic? Where you have a cosine, that's clearly periodic. Sine, that's clearly periodic. What about logarithm? Anything with a log in it or an exponential, you can tell that's not going to be periodic because of the way a log function looks. A log looks something like that. It's an increasing function. And e to the power t is increasing. E to the power minus t is decreasing. So those logs and exponentials won't be periodic. Unless you have a cosine or a sine that's written using Euler's formula. So e to the ix plus e to the minus ix over 2, for example. That is another way of representing cosine, so that would be periodic. What about sine t squared? So sine t, that's periodic. Sine t brackets squared, that would be periodic. But sine t squared, remember t, when you square it, it's no longer linear, and that wouldn't be periodic. So sine t squared wouldn't be periodic. Think about it, try it, see what it looks like. Once the independent variable t is squared, when you try to plot sine t squared against t, and the independent variable, this wouldn't be periodic. So for each of these, how would you find the period? What's the period of cosine 5t? Well, it's just 2 pi divided by 5, isn't it? And sine t minus 5, that period is just 2 pi, because sine and cosine, their periods are 2 pi. Remember, we talk in radians. In engineering, and this module in particular, we talk in radians, not in degrees. The next distinction we make is between even and odd signals, or even and odd function. An even signal or an even function is something that looks like a cosine in the sense that it's symmetric about the vertical axis. So about t equals 0. It's symmetric. What do I mean by symmetric? I mean that x of minus t is the same as x of t. So in this case, x of minus t here is the same as x of t there. So for example, cosine is even because cosine of minus 1 is equal to cosine of 1, because that's the way the function looks. It's even. An odd function is one that has a different kind of symmetry. It's still symmetric, but it's a different kind of symmetry. So it looks something like a sine wave, where x of minus t is negative x of t. So sine of minus 1 is the negative of sine of 1. You can check that by sketching a sine signal or by using your calculator. So any signal for which this holds, for all values of time, obviously, we call an odd signal or an odd function. So signals can be odd, signals can be even, or they can be neither odd nor even. They can't be both, but they can be neither. Now, if you add two signals together, if the two signals are periodic, will the sum also be periodic? That is a good question. It's a question I've asked in exams before, and it's a question that you'll see in your problem sheets, and it's a question that I'm answering right now. When you add two signals, let's say they're both periodic with fundamental periods T1 and T2, then the result may be periodic. And the condition is, if the ratio of T1 to T2 is a rational number, that means the ratio of integers, then it will be periodic. Otherwise, it's not periodic. So if you just think about it, sine t and sine 6t, they're both periodic, And T1 and T2, the two periods, you can find it's 2 pi and 2 pi over 6. So one is a multiple of the other. So the ratio of T1 over T2 is 6. So that's a rational number. Therefore, we can find the period of the sum of these two signals. Okay, so here's another example. X1 has a period of 4 milliseconds and X2 has a period of 3 milliseconds. Then if I add X1 and X2, I will be creating a periodic waveform. And the period, so why is it periodic? Because the ratio of 3 milliseconds to 4 milliseconds is rational. It's the ratio of integers. And if I take the lowest common multiple of 3 and 4, that's 12. So every 12 milliseconds, y of t will repeat. So that is the period. The period of x1 plus x2 isn't t1 plus t2. It's not 3 plus 4. It's the lowest common multiple. That doesn't always mean 3 times 4. It's the lowest common multiple. Now, another distinction we make in classifying signals is that between a deterministic signal and a random signal. A deterministic signal is one that we can describe mathematically. A random signal is one that we can't. So it doesn't mean, a random signal doesn't mean that it's totally random. It doesn't mean that it's meaningless. It doesn't mean that every sample is not correlated to the next. It just means that we can't represent it mathematically. So in that sense, my voice would be considered a random signal. A deterministic signal is a signal that you can represent mathematically. Let me show you a quick example of that. So here we have an AM signal. So this is a radio signal. So we have a high frequency carrier, we have a low frequency message, and one is modulating the other. We'll look at exactly what this means next semester when we study communications. But this is called a deterministic signal. Why is it deterministic? Because that's the expression for it. It can be represented mathematically. It also happens to be periodic because that point there is equivalent to that point there, which is equivalent to that point there. So you have a period that we can actually calculate. So that period we can calculate, and I can get it straight from there. So this is a deterministic signal that happens to be periodic, that happens to be analog, that happens to be continuous in time, but we're talking about the deterministic nature now. This is a random signal. Where have we seen this before? This is the radar signal from the subsurface radar that I showed you. So there is some structure to the signal, there is some meaning to the signal, it's just I can't represent it mathematically. I don't know the mathematical representation of that. So we consider that to be a random signal. Now the next distinction we make is between a causal and a non-causal signal. Again, this will become very important when we get to week 7. A causal signal is a signal that is only non-zero after t equals 0. So it's 0 before that. So can you think of a signal that's a causal signal? A signal that only starts its existence after t equals 0? Consider any experiment where you actually turn on the device, you turn on the power supply at t equals 0. Everything that you measure, you then measure after turning on the device. So at t is greater than or equal to 0. Because for negative time, we don't have any signal. So we just assume the signal doesn't exist or it's equal to 0. A non-causal signal is a signal that does exist for negative time. So you can probably think of many examples of causal signals and very few examples of non-causal signals, because all real signals tend to be causal. Non-causal signals mathematically exist, of course. A signal can exist for negative time or positive time. But depending on what t equals 0 actually means, that can be either a physical possibility or an impossibility. But mathematically, any signal which exists for negative time we call non-causal. So cosine t is a non-causal signal because it exists for negative time and it exists for positive time. Whereas a signal which would only exist for positive time, or t greater than or equals 0, we consider to be a causal signal. The final distinction I want to make is between energy and power signals. An energy signal is a signal that has finite energy and 0 average power. If you look at this signal, its energy is finite. If you were to integrate this signal squared over all time, it will be finite. But the power, the average power, if you were to divide the energy divided by time, and if you were to look at the entire time axis from minus infinity to infinity, the average power is 0. Compare that to this signal here. If you were to measure the energy, there would be an infinite amount of energy. So the amount of energy contained within this signal is infinite because it extends to t equals infinity, and it starts from t equals minus infinity. It extends over the entire time axis. But the power is finite. So if you measure the energy and you divide by the time that you did the measurement, you'll get something finite divided by something finite, and that ratio will be finite. So here the power is finite, but the energy is infinite. So we call this a power signal. So a cosine or a sine, these are examples of power signals. But any signal which is concentrated in time so that the signal diminishes to 0 as time approaches infinity and is 0 as time approaches minus infinity, we call that an energy signal because the energy is finite, it's limited, and the power, the average power, is 0. So just remember how these two look. So that is an example of an energy signal, and that's a good way to remember what an energy signal is like. So when we say energy, what do we mean? And the energy of a signal is simply the integral of the signal squared. Okay, so that signal x could be a voltage, could be a current. So remember, you know, what's the power of a signal of a potential difference V? It would be V squared over R, or if it was a current, it would be I squared R. So you take your signal, you square it, and you integrate it over the region of time you're interested in. So if you want the total energy, you integrate over the total time axis. That's how you find the energy of a continuous time signal. Why do I say continuous time? Because we're using integration. We use normal brackets, continuous time variable. This only applies to a continuous time variable, or continuous time signal. The power is exactly the same, except you need to divide by the time over which you're integrating. So if it's a periodic signal, and the period is uppercase T, then you integrate from minus T over T2 to T over 2. That means over one period. You could integrate from 0 to T. It doesn't have to be from minus T over 2 to T over 2. You can integrate from 0 to T, or from T to 2T, or from 10T to 11T, but you need to divide by the period you're integrating, and that'll give you the power. Now for a discrete time signal, that's where we use the square brackets and n is an integer. It's exactly the same, and instead of the integration, we're now using a discrete summation. Same here, instead of the integration, we're using the sum 0 to n minus 1. That ensures that you're covering a full period. So these are the equivalents to find the energy and to find the power for a continuous time signal and a discrete time signal. So as an example, if you had a signal like that, and the question was, calculate the total energy, you would simply integrate x of t squared over all time. As it happens, the signal is defined between minus t1 over 2 to t1 over 2. So you needn't integrate from minus infinity to infinity because it's 0 beyond that range. X of t is the amplitude there, it's a. So you square that, a squared. That's just a constant. What's the integration of a constant? It's just a squared t from minus t over 2 to t over 2. Substitute the limits and you get a squared times t1. So that is the energy of this rectangular pulse. Nice, easy example. There'll be many more examples in the problem sheet. Here we have a discrete time signal. You see, it's only defined for particular points in time. I've given you the formula here. So this is n, and this is 10 minus n. So now you know the formula for these two sections of the signal. And the question is, find the total energy. So instead of integrating x squared, we will use a discrete summation, x squared. So let's find the values. If this is n, then if t equals 1 or n equals 1, that's 1, 2, 3, 4, 5, and then 10 minus 5 is 5, 10 minus 6 is 4, 3, 2, 1. So you just add those together, but you square them first. So it's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and then again 4 squared, 3 squared, 2 squared, 1 squared. Add those all up, that gives you the energy of your discrete time signal. Okay, so we've done an example for energy for continuous and energy for discrete. Now moving on to something slightly different. We're going to go over this again next week, but there are 3 elementary functions we need to be aware of. Something called the unit step, something called the unit ramp, something called the unit impulse. So remember in this example where we had this ramp-like function that went up and then down, how could I represent that mathematically without using this messy notation like here? Instead of saying 3 periods of time, can I represent that mathematically? The answer is yes, but I need some more tools. I need some functions that we might not have used before. So there's this 3 functions: unit step, u of t, unit ramp, r of t, unit impulse, delta t. Now these are all the continuous time variants of these functions. There are also discrete time. So u bracket, square brackets of n, that will be the unit step in discrete time. Same with the ramp, same with delta, but we'll look at that a little bit later. So unit step is simply a signal that's always 0 for negative time and always 1 for positive time, or t greater than or equal to 0. So it's like flicking a switch, like turning on the light. It's 0 for negative time, and it's 1 for t greater than or equal to 0. So that's a mathematical tool that's going to come in really handy. A unit ramp is exactly that. It's the same as the unit step in the sense that it's 0 for negative time, but as soon as time becomes positive, r of t becomes positive and it increases proportionally. So r of t equals t. So at t equals 0, it's 0. At t equals 1, it's 1. At t equals 22, it's 22. So it's literally a ramp. And a unit impulse, or impulse function, or a Dirac function, is a slightly strange function. It's a function that's always 0. The only point in time when it's non-zero is when t equals 0. So it's 0 at all time, except when t equals 0, then its value is infinity. More about that in a minute. So again, remember the unit step? We said the unit step is like flicking a switch. But it turns out that the area under a unit impulse is actually 1. That's why we call it the unit impulse. Okay? So you might have been wondering, if the amplitude is infinity, why do you call it a unit impulse? It's because if you integrate a unit impulse over all time, the area is 1. Now, if you integrate it up to t, what you get is a unit step. So the unit step is the integral of a unit impulse. That means the unit impulse is the derivative of a unit step. And if you think about it, what's the derivative of 0? It's 0. What's the derivative of 1? It's 0 again. So that's the 0 here and the 0 there. And what's the derivative of this sharp increase, that rising edge between 0 and 1? It's rising between 0 and 1 in 0 time. So it's perfectly vertical. So the slope of that, the derivative of that, is infinite. That's why we say the unit impulse has a value of infinity at t equals 0. It's because that gradient, that derivative, that slope is infinite. But the area is 1. Now we can take a unit step and we can shift it to the right, or we can shift it to the left. By shifting it to the right, we subtract a constant from the independent variable t. That's a transformation you should be familiar with. It's called translation. Or we can shift it to the left by subtracting a negative number or by adding a positive number. That shifts it to the left. Okay, so by adding values to the independent variable t, you can shift your unit step to the left or to the right. So how would we describe this? That looks like a unit step, but something's wrong with it. It's upside down. We expect a unit step to start its life at 0 and then suddenly spring into action and come up to a level 1. But here it starts its life at 1 and then comes down to 0. So how would we do that? There's more than one way of doing that. If you think about it, what you can do is consider it to be a reflected and translated unit step. Reflected meaning left to right. So it's been flipped left, right. And then it's been shifted. So that negative sign, that creates the reflection. And that A, that creates the shift. So you want the rising edge or the falling edge in this example to be at t equals a. So if you substitute t equals a here, you'll have a minus a is 0, so u of 0. So what we want is this edge always to be when this argument here is 0. Okay, so this is a little example. Think about that. You might not be too comfortable with that at first, but don't move on until you are. Now, a unit ramp. Remember how we said that the unit step is the integral of the unit impulse? Well, the unit ramp is the integral of the unit step. And that probably makes sense to you, and you can probably see that unit step is the derivative of the unit ramp. So just look at that unit ramp. What's the gradient of that unit ramp? Well, it's 1. What's the gradient of t? It's just 1. So the gradient, the first derivative of the unit ramp, is the unit step. And if you were to take the area under a unit step, it would be a unit ramp. Okay, so r of t, we can write it as t times u of t, or we can just write r of t. Both of these are equivalent. Okay. So that was our first lecture. It took slightly longer than I anticipated. But what have we learned today? We've learned about the module and the structure and management of the module. We've learned about signals and systems and why they're important. We've gone through all the different classifications of signals. We've spoken about analog and digital and deterministic and random, periodic, non-periodic, deterministic and random, energy signals and power signals, discrete and continuous time signals. We've gone all through all those, and we introduced the elementary functions, and we'll talk more about that next time. Okay, so just as a reminder, next Monday you have a class test. The Monday after that, you have a problem class. So this is where we're at now. We just finished signal classification. Next week, we'll be talking about signal operations before we start talking about some more advanced concepts. A final reminder, this is the schedule. We are currently in week 1, but next Monday you have a home test. I will give you plenty of practice. There will be problem sheets with questions, with solutions. I will also give you a practice test before the test, so you will have a chance to see the format of the test and how it works, etc. But it all happens on Monday at 11 o'clock. That's the only time the test will be available. So you need to make sure you're logged in and you're online at 11 o'clock on Monday. Okay, so that's the end of today's lecture. I hope you all stay safe, and I look forward to seeing you on Monday.